Our group consists of me, Lucas McCarthy, Patrick Allen, and Shiloh Birkenfeld. We are all mechanical engineering students at the South Dakota School of Mines and Technology. And for our free project in our mechatronics class, we have chosen to fully automate a brake dynamometer that was once previously controlled by manual operation. A brake dynamometer, at the most fundamental level, is used to measure the braking performance of braking system components such as the rotor, calipers, brake pads, and the primary characteristics that you're looking at when measuring these, or when testing a system on a brake dynamometer, are the pad coefficient of friction versus temperature and how that behaves, how fast the rotor rejects heat based on varying velocities, which would need to be simulated within a wind tunnel ideally. Other important characteristics to pay attention to are if brake judder occurs, galling, which is chunks being removed from the rotor or the pad due to not a strong surface or pad to rotor interface, and other things that can cause the rotor or the pad to fail, causing catastrophic failure in a vehicle, whether it be a race car or a road vehicle. Our primary motivation for this project is rooted in the past couple years. We designed an aluminum metal matrix composite rotor for the Formula SAE team. It was an aluminum 2024 base material with a silicon carbide deposited on the surface of the aluminum. And it overall reduced the weight of the rotor by 50%. However, one of the problems that we've been having is after significant wear or at high temperatures, we experience shearing where the metal matrix composite is removed from the aluminum while on track, and this results in a failure. We have to replace the rotor completely, and it can cause further damage to the system if a piece were to get lodged and lock up the tire completely. Luckily, this has only happened once, and it happened at the very end of the autocross event at competition, so nothing serious happened, and we were able to replace the rotor and continue on. Alright, so the main components of the brake dynamometer system are, first, the motor. This is a 3-phase 10 horsepower AC motor. We use this motor primarily because it was available on campus to reduce costs. A motor this size would normally cost us around $600 if we had to buy it on our own. Also, it's a 10 horsepower motor because that is the smallest size that provides ample torque to get the flywheel up to the necessary RPM that we need for the on-track simulation, which would be the ultimate goal of this project. The next most important device is the driver. The driver allows us to communicate or to control the motor. Because it's a 3-phase, it requires a driver to control the RPM and when to tell it to coast, brake, slow down, all the controls essentially for the system. It also is what will allow us to read in sensor values and control the motor so that it will perform how we would like it to. The next most important device, or the component, is the flywheel. The flywheel's main goal is to simulate the kinetic energy that the brake rotor would need to dissipate in an on-track scenario. For our application, the required RPM for the flywheel is approximately 3,000 RPM, and that will simulate approximately a kinetic energy of 30,000 kilojoules. And then the next component we have is the brake rotor. The brake rotor is obviously the device we will be testing. It is mounted to the shaft that goes back through the motor. Normally the system would have sensors such as a thermocouple, an RPM sensor, as well as an infrared camera that would allow us to view the whole disc versus a thermocouple, which can only read essentially one radial distance from the center of the rotor, so it would require multiple tests to get a full data of the rotor. Alright, and then the other components of the system required are a master cylinder. This is what is used to actuate or to apply pressure to the brake fluid, which is then transferred to the caliper, and then the pads would squeeze on the rotor. To actuate the master cylinder in this scenario, since we aren't on a car, we have used a pneumatic actuator valve that will allow us to tell the system when to allow air into this chamber right here, which would then apply a moment about this pivot, applying a force to the caliper, or to the master cylinder, and then to the caliper. Because we can't control how much pressure is applied to the master cylinder and then to the caliper between individual applications, we would set the pressure at the most optimum deceleration, or the optimum pressure that would result in the fastest deceleration rate to simulate the on-track scenario. Just to mention, before, this was the Nuke valve that was used to switch the air for the master cylinder on and off. This was hooked up right about here in the same position. This would require the operator to be within mere feet of a disc that weighs approximately 50 pounds, spinning at 3,000 RPM, built by students. That is not necessarily the most rigid system in the world, and which results in very high potential casualties if the system were to fail. As you can see, the system in its current state is incomplete, and this is primarily due to a lack of funding. We were unable to secure the funds possible to get all of the components to complete the system. To actually complete the system, we would need approximately another $200 at most to complete it. That would include a LETCOM communications module, which would essentially snap in the lid of the driver and then plug into the driver itself. And what this would allow us to do is to communicate from the Click PLC to the driver using Modbus. This greatly expands our capabilities as far as reading in sensors, sending analog values to the driver, which we are currently unable to do right now, as the Click PLC is only capable of sending digital signals for the most part with very limited analog control, if not only one set value. Also, we are missing, we are unable to power up the machine at the moment. Currently, the power supply is an L1430P connection. However, all of the ones in the wall are L630, which is a 3-pin. This is a 4-pin, which we do not have the adapter for to plug it in. So we would need to secure an extension cord that can convert it from the 4-pin to the 3-pin. However, this component also costs $50, which at the moment we were unable to get the money for to complete the project on top of the other components. We would also need sensors, which would raise the price to more than $200, but to get it functioning, we would need approximately $200. To complete the project, we would need a thermocouple as well as an RPM sensor. This would allow us to gather all the information that we need to make, to perform an analysis on the rotor and the pad interface and how they perform together, as well as to analyze how the aluminum rotor breaks down during operation, and whether or not we can come up with a solution that will allow the aluminum rotor to be more reliable in the future. This year, as a result of the failures of the aluminum rotor, we've had to switch to a stainless steel rotor, which is significantly more expensive than the aluminum one. However, it is much more reliable and maintains a relatively constant heat on the track, giving us constant pad friction coefficients, and predictable driving is what the ultimate goal is. So in the end, we were unable to actually run the dynamometer to get results for the project. However, our group has plans over the course of the summer and probably into next fall semester to gather the required equipment necessary to complete the project so that the brake dynamometer can be used in the future by not only us for testing, but also by other camp teams or individuals doing research such as the Baja, Super Mileage, HPV, just to name a few.